For centuries, humanity looked up at the night sky, charting the predictable dance of stars and planets. We believed we understood the cosmic order that governed our universe. But beyond our familiar solar system, deep in the interstellar void, a profound secret lay hidden. Worlds unlike any we could ever imagine. These are planets that defy the very rules we thought defined planetary existence. Objects that should not be there, yet they absolutely are. NASA, with its powerful observatories, began to uncover them not in ones or twos, but in a staggering abundance across the galaxy. The scientific community was stunned. Every new detection challenged decades of established theory on planet formation and stellar systems. They are not bound to a star's comforting embrace, nor do they trace stable orbits. These are cosmic wanderers, adrift in the endless dark. Scientists call them rogue planets, free-floating planets, or even nomad worlds, a startling revelation that shook the foundations of astronomy. Our traditional view pictured planets forming within protoplanetary disks, orbiting their parent stars in orderly, gravitational dance. But the universe, it turns out, is far stranger than we dared to imagine. Full of impossible worlds that broke free or never knew a star's pull. Early estimates suggested they would be rare anomalies. Now, data indicates there could be trillions of these dark worlds in our galaxy alone. This sheer number forces a radical reevaluation of how planets are born and how many habitable zones might truly exist beyond a star's light. From icy giants to possibly rocky cores, these planets exist in perpetual night, their surfaces untouched by sunlight, bathed only in starlight. How do such worlds come to be? Are they ejected from nascent star systems, or do they form directly in the cold, sparse interstellar medium? For a long time, the very idea of such objects was debated, relegated to theoretical models, or dismissed as statistical noise. Advanced instruments and ingenious observational techniques, like gravitational microlensing, finally confirmed their startling existence. They are cosmic ghosts, practically invisible, revealing themselves only through the subtle bending of light from background stars. This discovery wasn't just a new category of celestial body, it was a fundamental shift, expanding our cosmic senses beyond imagination. The universe is not the neat, orderly place we once conceived. It is wilder, more chaotic, and infinitely more populous with planetary bodies. These rogue planets represent a vast, unexplored frontier, promising secrets about the very mechanisms that forge worlds. But how many of these hidden worlds truly exist, and what truly happened in the early universe to scatter them across the cosmos? The question hung heavy in the cosmic void. How did science begin to grasp the impossible existence of these rogue planets? It wasn't a sudden discovery. Instead, it was a gradual accumulation of perplexing anomalies, faint whispers from the deepest reaches of space that defied all known planetary models. Astronomers, peering through powerful telescopes, began to notice something peculiar happening to the light from distant stars. Occasionally, a star's light would brighten and then dim in an unexpected, symmetrical pattern. This was a gravitational microlensing event. Predicted by Einstein's theory of relativity, microlensing occurs when a massive object passes precisely in front of a more distant background star. The foreground object's gravity acts like a cosmic magnifying glass, bending and amplifying the background star's light as it passes. Initially, these events were often attributed to binary star systems or other known celestial bodies. The cosmos is full of strange phenomena. However, some of these lensing events displayed unique characteristics. The light curves were distinct, hinting at a different kind of foreground object. Specifically, the duration and intensity of the brightening often pointed towards objects far too small to be stars, yet too massive to be mere gas clouds. These enigmatic gravitational signatures were consistent with free-floating planetary mass bodies, planets untethered from any parent star. The first confirmed detections came from collaborations like the Optical Gravitational Lensing Experiment, or OGLE, and MOA. These wide-field surveys continuously monitored millions of stars in the dense central regions of our Milky Way galaxy. They were essentially fishing for these fleeting microlensing events, watching for any subtle change in stellar brightness. As the data accumulated, what was initially thought to be a rare curiosity began to emerge as a surprisingly common occurrence. More and more frequently, the unique light curve of a rogue planet would flash across their instruments, confirming their existence. The scientific community was cautiously intrigued. Could these signals truly be from planets wandering alone through the cosmos? The implications were immense, challenging long-held assumptions about how planetary systems form and evolve around stars. Planets were expected to be gravitationally bound, orbiting a sun. The idea of them existing in isolation was considered highly unlikely. Yet the evidence from these microlensing events was growing, becoming harder and harder to ignore or explain away. Sophisticated computer models were developed to analyze the precise shape of these light curves, revealing the mass of the unseen objects. Many of these calculations consistently pointed to masses comparable to Jupiter, Neptune, or even Earth, unmistakable planetary sizes. The sheer number of detected events started to paint a picture of a universe teeming with these nomadic worlds. It wasn't just a handful, it was potentially billions, perhaps even trillions, scattered between the stars, unseen by conventional methods. This uneasy realization forced astronomers to reevaluate fundamental concepts. Our solar system might not be the standard after all. The universe was proving to be far stranger and more dynamic than previously imagined, full of cosmic exiles. The scientific method, driven by observation, was slowly but surely compelling a radical shift in perspective. These early, indirect detections were the first crack in the rigid theories that defined our understanding of planetary systems. It opened a Pandora's box of cosmic questions, shaking the very foundations of astrophysics and planetology. Scientists weren't just discovering new planets, they were discovering a new kind of planet, operating under different rules. But how do these strange, sunless worlds come to be, torn from their stellar nurseries? The answers are even more surprising. The established order of planetary formation was clear. Planets grew within the protective embrace of a star's protoplanetary disk, forever bound by its gravity. Our solar system, with its neatly orbiting worlds, served as the quintessential example, guiding decades of astronomical theory and expectation. Every new exoplanet discovery seemed to reinforce this fundamental understanding. Planets revolved around their parent stars in predictable celestial dances. But then whispers began. Faint signals from the darkest corners of the cosmos hinted at objects that defied this elegant, star-centric narrative. These weren't planets orbiting distant suns. They were lone wanderers, detected only through fleeting gravitational distortions in spacetime. The first serious clues arrived from microlensing events, where a massive foreground object temporarily magnified a background star's light. Occasionally, these events showed peculiar, brief spikes, anomalies within anomalies, suggesting a smaller, unseen companion to the lensing object. For years, these subtle gravitational signatures were often attributed to binary stars, brown dwarfs, or even observational noise, easily explained away. The prevailing models simply had no room for planets that weren't tethered to a star, so alternative explanations always took precedence. Yet the number of these unusual microlensing events slowly but steadily accumulated, creating a persistent hum of scientific curiosity. Each new detection, though isolated, added another data point to an increasingly unsettling pattern: too many unexplained gravitational effects. Astronomers found themselves grappling with an uncomfortable question. Could these fleeting disturbances be something entirely different, something truly rogue? The scale of the objects causing these anomalous microlensing events suggested masses more consistent with planets than with small stars. But a planet without a star? The concept felt like a fundamental violation of the cosmic rules etched into textbooks and theories. Skepticism was strong. It was easier to assume a misinterpretation of data or an unseen, faint star than to tear down established paradigms. However, improved telescopes and more sophisticated analysis techniques began to make these anomalies harder and harder to ignore. The scattered detections coalesced, pointing towards a population of planetary mass objects that showed no evidence of stellar companionship. Some appeared to be moving freely, their paths untethered by any obvious gravitational master, drifting through the interstellar void. This growing body of evidence started to create visible cracks in the prevailing models of planet formation and evolution. The scientific community began to feel a subtle but undeniable pressure to reevaluate what was considered astronomically possible. What if planets weren't always born and bound within their stellar nurseries? What if some escaped or even formed differently? The observations hinted at a cosmic reality far more chaotic and diverse than our neatly organized solar system suggested. Each new data point chipped away at the old assumptions, forcing a difficult but necessary confrontation with the unexpected. It wasn't a single dramatic revelation, but a slow, creeping realization that the universe held secrets we hadn't accounted for. The tension mounted as astronomers faced the possibility that their foundational understanding of planetary systems was profoundly incomplete. The old rules, once unshakable, were starting to bend under the weight of these strange, solitary worlds appearing in the darkness. This wasn't just a discovery. It was the quiet genesis of a paradigm shift, an awakening to a new class of celestial bodies. They were out there, these free-floating objects, challenging our definitions and expanding the very boundaries of planetary existence. The scientific consensus, built over centuries, was on the cusp of a dramatic reevaluation, driven by these invisible cosmic rebels. But if these rogue planets truly shattered our understanding of where planets belong, then how exactly did they come to be? Following previous revelations, the most profound shock arrived. Worlds not merely in strange orbits but utterly unchained. The universe held planets truly alone. This discovery shattered a core assumption. For centuries, planets were defined by their star, a fundamental parent-child relationship in the cosmic nursery. How could a planet exist without a gravitational master? The very notion seemed to defy the cosmic order, challenging every known model of stellar birth. Detecting these solitary wanderers proved incredibly difficult. Unlike orbiting worlds, they offered no rhythmic wobble or periodic dimming to observe. Early hints emerged from rare gravitational microlensing events, a fleeting distortion of background starlight, revealing an unseen mass passing by. It was a monumental shift. Scientists realized these were not failed stars or brown dwarfs, but true planets adrift in the interstellar void. The implication was staggering. Millions, perhaps billions, of worlds might be traversing the galaxy in eternal darkness, without a home star. This forced astronomers to confront a radical question. How do planets form and then get violently ejected, cast out into the cold, silent depths? The sheer prevalence of these unbound worlds defied all initial predictions, suggesting our galaxy might be teeming with countless stellar orphans. What could these solitary wanderers teach us about planetary evolution, the violent birth of solar systems, and the true extent of life's possibilities? The most common theory suggests a violent cosmic dance as the primary culprit for these lonely wanderers, ejected from their chaotic birthplaces. Imagine a newborn star system, still swirling with vast clouds of dust and gas, where multiple giant planets are rapidly forming. In this incredibly chaotic and crowded nursery, these massive worlds don't immediately settle into stable, harmonious orbits around their star. Instead, they often engage in intense gravitational close encounters, a series of near collisions that reshape the entire system. A powerful gravitational slingshot from a massive sibling can impart enough momentum to hurl a smaller world out of its stellar home entirely. Once violently expelled, these unfortunate planets are cast into the interstellar void, adrift and forever separated from their parent star. This brutal eviction isn't a calm, natural drift. It's a testament to the destructive power within young, developing planetary systems. These rogue worlds are not accidents, but survivors, bearing the invisible scars of the chaotic, formative years of their birth. This process helps explain why astronomers are now finding so many rogue planets, far more abundant than anyone once believed possible. But if cosmic violence constantly throws planets into the dark, what happens to the star systems left behind after such a chaotic event? Imagine a world bathed in the warmth of its sun for billions of years. Then, in an instant, its star becomes a distant, fading point, shrinking against the black. The violent ejection process strips away its protective atmosphere, or at least severely damages it. No sun means no light, no heat, just an encroaching, absolute cold. Any liquid water on its surface would swiftly freeze solid, turning vast oceans into desolate expanses of ice. The once familiar landscape transforms into an alien realm. The vibrant hum of a planetary system, filled with gravitational echoes, vanishes. All that remains is the profound, terrifying silence of true interstellar space. This exiled world is now truly alone, a solitary sphere spiraling away from its birthplace. No more neighboring planets, no more shared orbital dance. It sheds its identity as a sun-warmed, active body. It becomes a spectral wanderer, an invisible ghost planet navigating the cosmic void in perpetual twilight. Scientists now understand that this isn't a rare anomaly. Billions of worlds have endured this catastrophic fate, silently roaming the dark between the galaxies. These aren't merely dead planets. They are survivors, resilient testaments to the universe's brutal forces. Each is a world carrying the scars of its violent past. Their existence forces us to reconsider the common narrative of planetary evolution. It shows systems are far more dynamic and violent than once assumed. But what secrets could such a deeply frozen, utterly isolated world possibly hold within its icy core? Can life persist in such unthinkable conditions? Scientists initially imagined these rogue worlds as frozen, barren rocks, eternally drifting in the frigid emptiness of interstellar space. A universe without light or warmth. However, emerging research suggests a more complex reality. Some rogue planets might possess enough internal geothermal heat from their formation to remain active. Deep within their rocky cores, radioactive decay could generate sustained warmth, defying the bitter cold of their surrounding cosmic void. Furthermore, a thick, insulating atmosphere, perhaps rich in hydrogen and helium, could trap this internal heat, much like a cosmic blanket. This protective atmospheric layer could prevent the rapid freezing of any subsurface liquids, creating entirely unexpected conditions on these wandering worlds. Beneath a perpetually frozen crust, vast oceans of liquid water, shielded by the planet's own gravitational pull, could potentially exist. These aren't just frozen remnants. These are active, dynamic subsurface environments, a stark contrast to their dark, cold exterior. This challenges our fundamental assumption that any planet ejected from its star must inevitably become a lifeless ruin. The universe is stranger. These hidden oceans, warmed from within, transform rogue planets from dead chunks of ice into potentially active, subterranean oases in the dark. If some rogue planets can maintain liquid water, then we must ask, could life, in some form, emerge or even thrive in these eternal cosmic wanderers? Far from any star, scientists now believe some rogue planets might retain enough internal heat from their formation or radioactive decay to warm their deep interiors. A surprising discovery in the cosmic void. Geothermal forces, similar to those on Earth, could still be active within these lightless wanderers. This prevents their cores from freezing solid entirely, against all prior expectations. This sustained warmth opens up an astonishing possibility: the existence of vast, hidden liquid water oceans, buried beneath colossal shells of ice and rock, far from any sun. These subterranean seas, perpetually dark and under immense pressure, represent alien environments unlike anything we've ever directly explored in our own solar system. Furthermore, many rogue planets could possess surprisingly dense atmospheres, thick enough to trap what little internal heat they generate, creating a greenhouse effect without a star. These protective gaseous layers would insulate the world below, preserving internal warmth and potentially allowing for complex chemical processes to unfold over billions of years. In these isolated realms, strange chemical reactions might be bubbling away, fueled by geothermal vents and pressure, creating unique molecular structures completely cut off from stellar radiation. Such worlds are far from the simple frozen chunks of debris scientists once envisioned. They are dynamic, geologically active bodies with their own hidden cycles and ecosystems. The potential for life, even microbial, existing within these buried oceans or unique atmospheric layers, pushes the boundaries of astrobiology into truly uncharted territory. These strange planets may force us to reconsider the very definition of a habitable zone, suggesting the universe holds far more hidden cradles of complexity than we ever dared to imagine. The idea of a rogue planet, adrift in the eternal night, hosting a subsurface ocean seems utterly impossible at first glance. Yet, scientific models suggest otherwise. Without a star, external heat is gone. But planets aren't simply cold rocks. They possess internal engines, remnants from their violent formation. Radioactive decay within a planet's core generates sustained heat. For some, past gravitational interactions could also leave residual tidal warmth. A thick, insulating shell of ice and rock acts like a planetary blanket, trapping this internal warmth and preventing it from radiating into space. Beneath immense pressure, water's freezing point changes. This, coupled with the internal heat, creates conditions where ice can melt, forming liquid water. Imagine a vast, deep ocean, kilometers beneath an icy crust, existing in perpetual darkness, untouched by sunlight or starlight. This doesn't require a fast process. For worlds large enough and with sufficient insulation, these buried oceans could persist for billions of years. Similar to the subsurface oceans found on icy moons orbiting gas giants, these rogue world oceans would simply lack the external stellar energy. The profound darkness of deep space, therefore, does not inherently signify a dead world. It merely redefines the parameters for activity and potential. If liquid water can persist for eons on these forgotten worlds, then the question inevitably shifts. What unknown geological processes, or even life, might lurk within their depths? This discovery isn't merely adding strange new worlds. It's forcing a fundamental reevaluation of planetary science itself. Our understanding of where life could exist is undergoing a radical transformation. For decades, the search for life centered on the habitable zone, that specific region around a star where liquid water might stably persist on a surface. This concept, foundational to astrophysics, presumed that a star's warmth was the sole energy source capable of sustaining such an environment. Rogue planets, drifting in the frigid emptiness far from any sun, seemed to defy every condition required for liquid water. They were considered dead worlds. Yet the potential presence of subsurface oceans on these cosmic nomads obliterates that traditional boundary. Internal geological heat, not stellar warmth, is the key. This internal energy, likely from radioactive decay or tidal heating if they once had companions, could keep vast amounts of water liquid beneath an icy crust. Such a revelation means the universe's true habitable zones extend far beyond the narrow bands around stars, encompassing the dark, interstellar voids. It implies that entire classes of planets, once dismissed as sterile, could potentially harbor environments conducive to life's emergence and evolution. The sheer number of rogue planets estimated to exist further amplifies this possibility, suggesting countless hidden biospheres might populate our galaxy. We are faced with a universe potentially teeming with liquid water worlds, existing in a state of perpetual night, yet alive with internal warmth. This dramatic shift challenges astronomers and astrobiologists to fundamentally rethink their search strategies and definitions of habitability. The old paradigm, limited to sun-warmed surfaces, is giving way to a more expansive, subterranean vision of potential homes for extraterrestrial life. Rogue planets are no longer mere gravitational curiosities. They are becoming crucial laboratories for understanding planetary evolution under extreme conditions. They demand that we consider how life might adapt and thrive in environments utterly alien to Earth's sun-drenched surface, under miles of frozen shell. What fundamental principles of planetary formation and the distribution of life are these dark, ocean-bearing wanderers now forcing us to redefine? The very idea of life thriving without the warmth of a star feels alien, almost impossible. Yet, as we delve deeper into rogue planets, this seemingly outlandish concept gains surprising scientific traction. The key lies not in stellar light, but in primordial heat. Many rogue worlds retain significant warmth from their formation, generated by radioactive decay and gravitational compression deep within their cores. For some, particularly if they formed with large moons, ongoing tidal forces could also provide a consistent, internal energy source, much like Jupiter's moon Io. This internal geothermal energy is crucial. It's enough to maintain liquid water far beneath a planet's icy crust, creating conditions strikingly similar to some of Earth's own extreme environments. Think of our planet's hydrothermal vents, teeming with life in perpetual darkness, fueled by chemosynthesis rather than sunlight. Rogue planets could harbor analogous ecosystems. Beyond internal heat, a dense, insulating atmosphere could play a vital role. Such an atmosphere could trap whatever warmth exists, preventing it from radiating away into the cold void of space. Gases like hydrogen or helium, if sufficiently abundant, could create a powerful greenhouse effect, maintaining stable temperatures on the surface or within subsurface oceans, even in profound darkness. This thick atmospheric blanket also offers protection from cosmic radiation, shielding any potential life forms from the harsh, unfiltered energies prevalent in interstellar space. These deep, dark oceans, insulated by kilometers of rock and ice, become sanctuaries. They are stable environments, protected from the extreme temperature fluctuations of the surface. Within these hidden seas, interactions between water and a rocky core could provide the necessary chemical building blocks and energy gradients for complex biochemical reactions to unfold. Scientists are now exploring models where such conditions, sustained over billions of years, could be conducive to abiogenesis, the spontaneous emergence of life from non-living matter. Life here would not rely on photosynthesis. Instead, it would evolve entirely around chemosynthesis, drawing energy from chemical reactions, leading to truly unique biological forms. This paradigm shift fundamentally alters our understanding of habitability. Life isn't exclusively a sunlit phenomenon. It might be far more resilient and adaptable than we ever imagined. If rogue planets are indeed viable cradles for life, the cosmic landscape of potential biological worlds expands exponentially, beyond the narrow confines of stellar systems. But how do we even begin to detect these hidden worlds and search for signs of such alien life in the vast, cold emptiness between stars? The profound question lingers. Could these isolated, dark worlds fundamentally redefine our quest for extraterrestrial life across the cosmos? For millennia, humanity assumed stellar energy, the warm embrace of a sun, was a non-negotiable prerequisite for any complex planetary activity. Yet, rogue planets challenge this bedrock assumption, hinting at alternative energy sources radiating from within their very core. Radioactive decay and tidal stresses, unseen from afar, could provide enough geothermal heat to sustain vast subsurface oceans. Imagine lightless depths, kept liquid by internal warmth, mirroring the hydrothermal vent systems teeming with life on Earth. These deep-sea vents release superheated, mineral-rich fluids, creating vibrant chemical gradients that power entire ecosystems. On rogue planets, chemosynthesis, life fueled by chemical reactions, could be the dominant energy pathway for resilient microbes. This means a planet doesn't need to orbit a star to be considered a potentially habitable world, dramatically expanding the search. Scientists are now actively modeling these unique conditions, probing the potential for complex chemical environments beneath icy crusts. The universe might harbor countless pockets of life, thriving in the absolute darkness of interstellar space, untouched by starlight. This radical paradigm shift compels astrobiologists to reconsider where and how life could arise, far beyond our solar system's confines. These rogue worlds are no longer just cold, barren remnants, but intriguing habitats potentially fostering ancient, isolated ecosystems. Future missions and advanced telescopes will be instrumental in exploring the chemical signatures of their hidden atmospheres and oceans. What was once dismissed as a cosmic anomaly is now emerging as a serious scientific frontier, pushing the boundaries of discovery. Could the next great revelation in the search for life come not from a star-kissed world, but from the depths of a lonely wanderer? The possibility of hidden oceans and sustained geothermal activity fundamentally redefines what makes a world scientifically significant. We must consider their true potential. These dark wanderers, once dismissed as barren cosmic accidents, could harbor conditions suitable for life, far from the warmth of any star. Deep beneath their icy crusts, tidal forces or radioactive decay could generate enough heat to sustain vast liquid water reservoirs for eons. This internal energy drives complex chemical reactions, creating a dynamic environment where the very building blocks of life might assemble, independent of sunlight. This paradigm shift challenges our traditional Earth-centric view of habitability, expanding the cosmic real estate where life could potentially flourish. We're no longer confined to planets orbiting within a star's narrow habitable zone. Life could thrive in entirely new niches, unseen and unexpected. The search for extraterrestrial life must now broaden its scope dramatically, including these sunless, isolated worlds among its most promising targets. Scientists are beginning to view rogue planets not as mere anomalies, but as a potentially numerous class of astrobiological importance. Given their estimated abundance, if even a small fraction of them are habitable, the universe could be teeming with such hidden ecosystems. Understanding these rogue worlds helps us grasp the full diversity of planetary evolution and the varied pathways life might take across the cosmos. No longer just frozen, ejected debris, these planets are emerging as dynamic, potentially living entities, full of surprising potential. The challenge now lies in developing the technology to detect these internal oceans and measure their chemical signatures from vast interstellar distances. Future space missions might one day target these dark nomads, sending probes to plunge beneath their frozen shells in search of liquid water. This reevaluation positions rogue planets at the forefront of astrobiology, proving their scientific worth extends far beyond mere celestial curiosity. But what specific signs and biosignatures should we look for on such sunless worlds? And how do we even begin to detect them from light years away? The unsettling truth begins to emerge. The galaxy may indeed be teeming with hidden worlds, far beyond what our current observations suggest. For decades, our understanding of planetary systems was shaped by what we could directly see, planets orbiting their parent stars. Rogue planets were once considered rare cosmic anomalies, statistical outliers in the vast dance of stellar evolution. Early estimates suggested their numbers might be negligible compared to the billions of star-bound worlds we've cataloged. However, as our detection methods grow more sophisticated, a staggering new picture is beginning to materialize. The limits of our technology mean we only ever glimpse the brightest, largest, or closest of these nomadic bodies. There exists an immense, unseen population, a dark census of planets that drift silently through the cosmic abyss. Scientists now estimate that for every star in our galaxy, there could be thousands of these free-floating planets. Imagine a cosmos where the lone wanderers outnumber the stars themselves, a truly mind-boggling scale of worlds. Our own Milky Way could host trillions of these unseen planetary bodies, a number that utterly dwarfs previous assumptions. These estimates are largely based on indirect observations, subtle gravitational influences on distant light sources. This overwhelming abundance suggests that the ejection of planets from nascent star systems might be a common rather than rare event. It forces us to consider a universe where the norm is not a cozy orbit, but an endless, solitary journey through interstellar space. Billions upon billions, a hidden ocean of worlds, shaping the very dynamics of the galaxy in ways we are only now realizing. But if these rogue planets are so incredibly common, what advanced techniques will it take to truly reveal their full extent? The very nature of rogue planets makes them almost impossible to spot. Drifting free from any star, they emit virtually no light of their own, becoming ghosts in the cosmic void. Without a star's intense glare to illuminate their surfaces, these solitary worlds simply fade into the background. They are cloaked in a profound, almost absolute blackness. Any faint light they might reflect from distant stars is incredibly weak, like a whisper in a thunderstorm. Our current telescopes struggle immensely with such faint signals. From Earth, even the largest and most powerful observatories are essentially looking for a needle in a cosmic haystack, a dark needle against an equally dark backdrop. Space itself is incredibly vast, a gulf of nothingness, where these worlds can wander for eons without crossing paths with anything significant enough to reveal them. This leads to an unsettling thought. Could massive, ice-cold worlds be moving through our galactic neighborhood right now, completely bypassing our watchful eyes? Imagine a planet-sized object, many times the mass of Earth, silently approaching and then receding, its presence never betrayed by a single photon of light. These aren't static objects. They are traveling at immense speeds, following paths influenced by the subtle gravitational tugs of unseen masses throughout the galaxy. Our primary detection methods often rely on gravitational lensing, or brief occultations of background stars. These are rare events, not routine surveys. Given the estimated billions of rogue planets, the probability that many are constantly traversing interstellar space, undetected, becomes chillingly high. We picture the cosmos as filled with glowing stars, but much of its mass hides in plain sight, utterly invisible, wandering through the profound emptiness. It's like standing in a darkened room, knowing there are others around you, but unable to see their movements, only sensing their potential presence. These worlds could be passing us right now, vast, cold bodies on an endless journey, offering no hint of their existence until it's far too late to observe. This changes our perception of the night sky from a canvas of light to a deeper, more mysterious ocean, teeming with silent, wandering behemoths. If these invisible worlds are so common, could one get close enough to leave an undeniable mark, even without ever being directly seen? The unsettling truth is, our current methods for detecting these solitary wanderers are severely limited. They emit no light of their own and orbit no star. This makes them virtually invisible against the vast, dark canvas of interstellar space, even if they were relatively close by. Imagine a colossal gas giant, like Jupiter, drifting silently, just a few light years away. We might never even know it was there. For us to spot it, it would need to pass directly in front of a distant star, causing a momentary dip in its light, a rare alignment indeed. This means that what we perceive as vast, empty cosmic voids between star systems could, in fact, be teeming with hidden worlds. They are the dark matter of planetary systems, a silent, unacknowledged population of gravitational behemoths shaping the universe. So the question isn't just how many rogue planets exist across the galaxy, but how many might be much closer to our own solar system. What if one or more massive rogue planets are currently traversing the Oort cloud, the distant icy shell that surrounds our sun? They would be too dim to see, moving too slowly to easily detect, a silent ghost in our cosmic backyard, influencing unseen dynamics. The sheer volume of space we'd need to meticulously survey for these faint, elusive objects is staggering, a true needle in a cosmic haystack. This fundamentally shifts our perception of what lies beyond the familiar glow of our sun and the nearest stars. It's not empty. It's a chilling thought that monumental planetary bodies, perhaps even larger than Earth, could be drifting past us, unseen for millennia. Our solar system has likely experienced countless close encounters with such wanderers throughout its long history, leaving no discernible trace. Only with next-generation observatories, specifically designed to detect these faint gravitational lenses, might we truly map our cosmic neighborhood. But if these invisible worlds are truly so common, so close, what impact might they have had on the very formation and evolution of our own planetary home? The vastness of space makes spotting these dark wanderers incredibly challenging, even if they are relatively close. They reflect almost no light, merging seamlessly with the cosmic void around them. Unlike planets orbiting stars, these rogue worlds lack a constant illumination source. Their surfaces remain cloaked in perpetual night, absorbing stray photons rather than scattering them for our instruments to detect. Our most powerful telescopes are designed to capture faint starlight or the reflected glow from distant galaxies. They struggle to find objects that actively avoid revealing themselves in the visible spectrum. Imagine a silent, massive sphere, darker than coal, hurtling through the interstellar medium. Without a stellar beacon to outline it, it becomes indistinguishable from the background, a true cosmic ghost. These wanderers move at incredible speeds, often on unpredictable trajectories. A rogue planet could traverse vast distances across the galaxy, passing through star systems with only a fleeting, barely noticeable presence. A close pass by one of these invisible giants might manifest only as a subtle gravitational tug on nearby stars or gas clouds, a silent disturbance in the cosmic fabric. It would leave little other trace. Even if a rogue world approached our solar system, its dark nature means it wouldn't blaze like a comet or reflect sunlight like a regular planet. It would remain an almost perfectly hidden sentinel. This unsettling reality forces us to confront the possibility that large, planetary mass objects could be moving through our galactic neighborhood completely undetected, silent nomads of the void. Our current observational methods are largely site-dependent, biased towards the luminous and the illuminated. Rogue planets defy this bias, thriving in the profound darkness of interstellar space. The question then shifts: if they are so incredibly difficult to spot, how could we ever truly map their presence or predict their silent journeys across the cosmos? The vastness of space makes spotting these dark wanderers incredibly challenging, even if they are relatively close. They reflect almost no light, merging seamlessly with the cosmic void around them. Unlike planets orbiting stars, these rogue worlds lack a constant illumination source. Their surfaces remain cloaked in perpetual night, absorbing stray photons rather than scattering them for our instruments to detect. Our most powerful telescopes are designed to capture faint starlight or the reflected glow from distant galaxies. They struggle to find objects that actively avoid revealing themselves in the visible spectrum. Imagine a silent, massive sphere, darker than coal, hurtling through the interstellar medium. Without a stellar beacon to outline it, it becomes indistinguishable from the background, a true cosmic ghost. These wanderers move at incredible speeds, often on unpredictable trajectories. A rogue planet could traverse vast distances across the galaxy, passing through star systems with only a fleeting, barely noticeable presence. A close pass by one of these invisible giants might manifest only as a subtle gravitational tug on nearby stars or gas clouds, a silent disturbance in the cosmic fabric. It would leave little other trace. Even if a rogue world approached our solar system, its dark nature means it wouldn't blaze like a comet or reflect sunlight like a regular planet. It would remain an almost perfectly hidden sentinel. This unsettling reality forces us to confront the possibility that large, planetary mass objects could be moving through our galactic neighborhood completely undetected, silent nomads of the void. Our current observational methods are largely site-dependent, biased towards the luminous and the illuminated. Rogue planets defy this bias, thriving in the profound darkness of interstellar space. The question then shifts. If they are so incredibly difficult to spot, how could we ever truly map their presence or predict their silent journeys across the cosmos? The idea of a truly alien world, a rogue planet drifting into our solar system, feels like science fiction. Yet, with so many discovered, such cosmic encounters are a statistical possibility. Imagine a dark, icy sphere, hundreds or even thousands of miles across, approaching from the interstellar void. It emits no light, reflecting only the faintest starlight back towards us. Spotting such a stealthy object from afar is incredibly difficult. Even if observed by distant telescopes, its trajectory would remain elusive, a true wanderer with unpredictable motion. As it crosses the outer reaches, perhaps the Oort cloud, its gravity begins to subtly pull on billions of icy bodies. Some could be sent on new, dangerous paths toward the sun. Further inward, its gravitational influence intensifies. The massive gas giants, usually stable, would feel a slight, unsettling tug sending ripples of instability through their orbits. A close enough pass could perturb the delicate balance of the inner solar system. Asteroids and comets might be dislodged, increasing collision risks with terrestrial planets exponentially. The precise outcome depends on the rogue planet's mass, its speed, and its exact trajectory. But even a seemingly small gravitational nudge has profound, cascading effects over cosmic timescales. Scientists actively model these terrifying scenarios, exploring the chaotic dance of gravity when a foreign body interrupts established planetary order. It's a cosmic game of billiards. The primary threat isn't necessarily a direct impact, but the long-term orbital instability it could unleash across our entire solar system. Chaos could reign for millennia. So, how prepared are we for such an improbable, yet potentially catastrophic event? What mechanisms exist to detect and track a truly dark wanderer before it impacts our future? Our long-held perception of planetary systems as stable, predictable clockworks, with planets orbiting their stars in perfect harmony, is now being challenged by every new rogue world we detect. These free-floating planets are not just cosmic anomalies. They are stark reminders that gravitational balances within nascent star systems are often tenuous, easily disrupted by passing objects or internal dynamics. In the turbulent early days of a stellar nursery, gravitational interactions are fierce. Massive protoplanets jostle for position, their immense pull capable of catapulting smaller siblings into the void. An orbital path, once secure, can become a trajectory of no return. A slight nudge, a shift in mass distribution, or a close encounter can send a world spiraling towards the ultimate escape velocity. Each ejected planet represents a seismic event in its home system's history. It's a testament to the system's inherent instability, revealing that even established structures can crumble. What once seemed like a rare, violent exception to planetary formation, is now understood as a common, often inevitable, phase in the lives of countless star systems across the galaxy. The delicate dance of gravity, keeping planets bound to their star, is a precarious ballet. Even minor shifts in mass or external forces can irrevocably alter the system's choreography. The neat, concentric circles we imagine around distant suns are perhaps just temporary snapshots. Beneath the calm exterior lies a potential for chaos, a universe of dynamic, shifting forces. This unsettling realization extends to our own solar system. While seemingly stable, it too is subject to the same cosmic laws of gravitational push and pull, constantly evolving over unimaginable timescales. Rogue planets compel us to rethink not just their existence, but the very definition of a stable planetary system. Are they truly stable, or merely existing in a transient state of delicate balance? This isn't just about planets being ejected. It challenges our fundamental view of cosmic order. What if the universe isn't biased towards stable, predictable systems, but rather embraces a violent, chaotic dance? From their very birth, planetary systems are battlegrounds. Young stars blaze, their gravitational tug-of-war ripping apart protoplanetary disks, forging worlds only to send them hurtling away. Close encounters between massive gas giants, the unpredictable dance of newly formed bodies, these are not rare events. Gravitational slingshots could be a common mechanism for cosmic exile. For every world nestled safely in orbit, countless others might lose the cosmic lottery. They are the unfortunate ones, condemned to drift endlessly through the dark abyss, forever lost. Our own solar system, with its harmonious orbits, might simply be an anomaly. A fleeting moment of calm in a universe where disruption and scattering are the dominant forces shaping planetary destiny. The neat, predictable clockwork we observe could be temporary. Planetary systems might evolve, grow unstable, and eventually shed their members like a dying star sheds its outer layers. Rogue planets, then, are not just curiosities. They are the tangible evidence of this messier universe, the lost children testifying to a violent history that most planetary systems endure. Perhaps the normal state of a planetary system isn't long-term stability. Instead, it's a dynamic, ever-changing environment where ejections are an integral part of its evolutionary path. This forces us to reevaluate our foundational assumptions. Are we looking for order in a cosmos that naturally tends towards chaos? The universe might be far more brutal than we imagined. What if rogue planets are not the exception, but a glimpse into the true, chaotic adolescence and eventual fate of most planetary systems across the vastness of space? These free-floating worlds, adrift in the cosmic void, aren't just strange outliers. Scientists now see them as cosmic scars, grim evidence of the brutal birth process of planetary systems. Imagine a young stellar nursery, not a peaceful cradle, but a swirling maelstrom of gas, dust, and countless protoplanets. Collisions are not exceptions, they are the rule. Within this chaotic cloud, massive young planets gravitationally wrestle with each other. Close encounters are inevitable, leading to powerful slingshot effects that launch smaller bodies. These gravitational kicks are immense. A developing giant planet, in a violent interaction with its siblings, can hurl a smaller, still-forming world entirely out of its solar system. This isn't an accidental anomaly. Modern simulations reveal that the ejection of planets is a common, perhaps even necessary, byproduct of planetary system formation. These lost worlds, expelled from their parent stars, are precisely the rogue planets we are now detecting. They are cosmic refugees, bearing witness to their system's turbulent past. Far from serene, early solar systems are arenas of intense violence. Collisions can shatter nascent worlds, creating debris fields or disrupt orbits, sending planets spiraling outward. Rogue planets are therefore not merely oddities, they are like astronomical fossils. Each one preserves a dark record of destruction, a planetary history written in gravitational chaos. Their existence forces us to reconsider our own solar system's relatively stable history. Was our system also once far more violent, with planets lost to the void? Understanding these rogue worlds means understanding the brutal adolescence of all planetary systems. What if our galaxy is truly littered with these silent reminders of destruction? These free-floating worlds, adrift in the cosmic void, aren't just strange outliers. Scientists now see them as cosmic scars, grim evidence of the brutal birth process of planetary systems. Imagine a young stellar nursery, not a peaceful cradle, but a swirling maelstrom of gas, dust, and countless protoplanets. Collisions are not exceptions, they are the rule. Within this chaotic cloud, massive young planets gravitationally wrestle with each other. Close encounters are inevitable, leading to powerful slingshot effects that launch smaller bodies. These gravitational kicks are immense. A developing giant planet, in a violent interaction with its siblings, can hurl a smaller, still-forming world entirely out of its solar system. This isn't an accidental anomaly. Modern simulations reveal that the ejection of planets is a common, perhaps even necessary, byproduct of planetary system formation. These lost worlds, expelled from their parent stars, are precisely the rogue planets we are now detecting. They are cosmic refugees, bearing witness to their system's turbulent past. Far from serene, early solar systems are arenas of intense violence. Collisions can shatter nascent worlds, creating debris fields or disrupt orbits, sending planets spiraling outward. Rogue planets are therefore not merely oddities, they are like astronomical fossils. Each one preserves a dark record of destruction, a planetary history written in gravitational chaos. Their existence forces us to reconsider our own solar system's relatively stable history. Was our system also once far more violent, with planets lost to the void? Understanding these rogue worlds means understanding the brutal adolescence of all planetary systems. What if our galaxy is truly littered with these silent reminders of destruction? These free-floating worlds, adrift in the cosmic void, aren't just strange outliers. Scientists now see them as cosmic scars, grim evidence of the brutal birth process of planetary systems. Imagine a young stellar nursery, not a peaceful cradle, but a swirling maelstrom of gas, dust, and countless protoplanets. Collisions are not exceptions, they are the rule. Within this chaotic cloud, massive young planets gravitationally wrestle with each other. Close encounters are inevitable, leading to powerful slingshot effects that launch smaller bodies. These gravitational kicks are immense. A developing giant planet, in a violent interaction with its siblings, can hurl a smaller, still-forming world entirely out of its solar system. This isn't an accidental anomaly. Modern simulations reveal that the ejection of planets is a common, perhaps even necessary, byproduct of planetary system formation. These lost worlds, expelled from their parent stars, are precisely the rogue planets we are now detecting. They are cosmic refugees, bearing witness to their system's turbulent past. Far from serene, early solar systems are arenas of intense violence. Collisions can shatter nascent worlds, creating debris fields or disrupt orbits, sending planets spiraling outward. Rogue planets are therefore not merely oddities. They are like astronomical fossils. Each one preserves a dark record of destruction, a planetary history written in gravitational chaos. Their existence forces us to reconsider our own solar system's relatively stable history. Was our system also once far more violent, with planets lost to the void? Understanding these rogue worlds means understanding the brutal adolescence of all planetary systems. What if our galaxy is truly littered with these silent reminders of destruction? The universe, it turns out, is far more filled with secrets than we ever imagined. Worlds cast adrift, unseen for eons, challenging our very perception of what a planetary system can be. These rogue planets are not mere curiosities. They are echoes of cosmic violence, vast gravitational slingshots that rip them from their stellar parents, condemning them to eternal night. Their existence paints a chaotic picture of planet formation, where expulsion and destruction are as common as the stable orbits we once assumed were the norm for all celestial bodies. Billions, perhaps trillions, of these dark wanderers traverse the interstellar void. A silent, cold majority, outnumbering the stars themselves, hidden within the endless depths of space. They force us to reconsider the tidy models of solar systems, unveiling a cosmos where rogue elements might be the rule, not the exception, in the grand cosmic design. What secrets do these isolated spheres hold? Are they barren wastelands, or do some harbor unimaginable conditions for life, fueled by internal geothermal heat, far from any star? Their discovery cracks open the serene veneer of the universe, revealing a deeper, more turbulent reality. A cosmos less predictable, more primal, and vastly more indifferent to order. This unsettling truth reshapes our cosmic address. We are not just dwellers of a stable, star-bound system, but part of a galaxy teeming with invisible, untethered worlds. Rogue planets are the universe's ultimate secret keepers, silent witnesses to formation's chaos, forever drifting through the cosmic night, defying our expectations of existence. They are the dark worlds we were never meant to notice, yet now, their profound silence whispers the true, haunting story of the universe's unpredictable heart.